So our ultimate goal is to calculate the enthalpy of vaporization of water. The way we're going to do that is we're going to measure the vapor pressure of water at various temperatures. So our experimental setup is very, very easy. We're going to have a container of water that we fill with a bunch of water, and then we're going to have an inverted graduated cylinder inside of our large container of what's going to be ice water. And initially, we're going to have, so we have this pocket of gas above the liquid water. So we're going to start out with very cold water, such that in this little pocket of air, what's this gas phase pocket, it's only air, because we're assuming the vapor pressure of water at that temperature, near 0 degrees Celsius, the vapor pressure of water is pretty much 0. What that allows us to do is to calculate the total number of moles of air in that gas phase pocket. Now, as we heat our container, what's going to happen is some of that water, that liquid water, is going to evaporate, and our total pressure of all the gas in that space increases. It's going to be the pressure of the air and the pressure of that water vapor. And this pressure of the water vapor is technically the vapor pressure of water at that temperature, which is what we're trying to get, is this number here. Since we know the number of moles of air from before, we can calculate what that new pressure of the air is at that new temperature. And then subtracting, knowing the total pressure, which is just going to be atmospheric, subtracting that new air pressure at the new temperature from the total pressure, we can calculate the vapor pressure of water at that temperature. So here's our data sheet. So as you can see, when we're going to start, we're going to have an initial temperature and observe volume. And of course, we have to correct that volume because of that inverted meniscus. And then we have our calculation cells. So the yellow ones are, of course, our data cells. So from this initial data, our initial cold temperature, we know the pressure coming from the air, we know the temperature of the air, we know the volume of the air, and we assume that the vapor pressure of water is 0. So that means we can calculate the number of moles of air. And this is going to be a constant for this particular run. That's just the number of moles of air in that little gas phase pocket from the beginning until the end. We have to account for it because, remember, so here we have our higher temperatures. As we're heating it up, obviously the volume is increasing because we are getting more and more gas. We have our new temperatures, and our pressure coming from the air can be calculated because now we know the pressure, we know the temperature of the air, we know the volume of the air, which is going to be the same as the volume of the water, and we know the number of moles of air. So we can calculate that new air pressure at that new temperature. We'll know what atmospheric pressure is, and the difference between these two, the pressure of the air and the total pressure, will give us our pressure of water at that particular temperature. And then we have our other columns for doing our graph. That's it.